When I was 10 years old, I used to live in Shepherd's Bush in West London. And every Saturday afternoon, I used to go to Shepherd's Bush Market. You see, I was very keen to see what people were buying, what they were selling, but most importantly, what they were throwing away. Because frequently, among other people's rubbish, I could find something useful for myself. For instance, a wooden box from which I could make a cricket bat. But every Saturday afternoon at Shepherd's Bush Market, there was a very strange man. He was selling medicine. He was selling medicine in little bottles like this, purple tablets in little bottles like this. And he told everyone that this medicine was the best medicine in the world. It could cure you of any problem which you might have. A headache, toothache, muscle pain, rheumatism, neuralgia, even nostalgia. This would cure your problem. And the reason why he said this would cure your problem is because, unlike many other medicines, this does not contain any acid. And everyone knows that acids burn. Now, he had some examples of medicines that contain acids to show to the people. He had, for example, a tin of Birdall's Seidlitz powders. Now, these are used to treat constipation. Read the label on the side. These contain tartaric acid. Acids burn, he would say. And then he had some Andrew's liver salts. Andrew's liver salts are used to treat indigestion. Read the label on the side. These contain citric acid. Acids burn, he would repeat. And then he had some aspirins. Aspirins used for headaches, migraines, muscle pain, etc. He took the label, he read it, and he said, this contains acetyl salicylic acid. Rather than telling you what this could do in your stomachs, he said, I am going to show you. So people were very curious to know what he was going to show them. He took out 2 tablets and he placed them on the palm of his hand. He put the tablets on the palm of his hand like this, and then he placed them onto some dark purple crystals. So allow me now to place the tablets, and he had these dark purple crystals. I will shortly show you them slightly up in the air, just a little closer up like that, and he put them on those crystals like that. So there are the aspirin tablets you see on the dark purple crystals. This was out in the open air at Shepherd's Bush Market. And then he said, when you are suffering from a headache or a toothache, it is entirely possible that you might also have a sore throat, in which case you might like to take some cough syrup. And he had a bottle of Sanatogen baby cough syrup, and he put some of that on top of the aspirins. And then he said, when you have taken these medicines, you may not like their taste, in which case you might like to drink some water. So he sprinkled some water. Now at this stage, people were absolutely amazed. They said, what on earth is going on here? What can there possibly be about these medicines which contain acid that can burn a hole in your stomach? And then suddenly it started steaming. And then suddenly the scene turned into smoke. And suddenly the whole thing burst into fire and started burning. Now when people saw this, they were absolutely terrified. And they said to themselves, I don't want to have that happening in my stomach. So do you know what they did? They started fumbling and bumbling around in their pockets until they found one of these. Now this, my dear friends, is 2 shillings and 6pence. It's half a crown. That is a lot of money. And every Saturday afternoon at Shepherd's Bush Market, everyone used to buy the magic medicine man's magic medicine. But not me. You see, I was very fortunate, because when I was 10 years old, I was never ill. So I didn't need the medicine. And I didn't have any money in any case, so I couldn't buy it. But I do have to tell you that ever since I had been a tiny baby, I had developed a serious psychological malfunction. I had developed a secret and passionate obsession with fire. Now, my parents had bought me a chemistry set when I was 8 years old. And I used to mix all the ingredients together in the chemistry set in an attempt to make fire. But all I succeeded in making was fizzes, pops and smells and smoke. Nothing like the magic medicine at Shepherd's Bush Market. So I decided I would try to repeat his experiment. Now, I knew where I could get the aspirins from. They came from Boots the chemist in Uxbridge Road. I knew where I could get the Sanatrogen baby cough syrup from. That too came from Boots the chemist in Uxbridge Road. But what I didn't know is, and I knew where I could get the water from, of course, and that came from the tap. But what I didn't know was the identity of those purple crystals. So I decided to find out. I went along to Shepherd's Bush Library, and there I borrowed a book which was called Chemistry Magic. And in that book, I started reading all the recipes for making fireworks mixtures, pyrotechnic mixtures, to see whether there was ingredients in those mixtures which fitted the description of those purple crystals. And do you know what? There was such an ingredient. It was called potassium permanganate. So together with the other medicines, I procured some potassium permanganate. I set up the experiment in my mother's kitchen at 44 Stanley Road, Shepherd's Bush, London, W12. And lo and behold, within half a minute, the whole thing burst into flames and filled the entire kitchen with smoke. That, my dear friends, was the greatest moment of my life. For it was my first ever truly successful chemistry experiment. And I have to tell you that ever since that day, I have been conducting chemistry experiments on an everyday basis. And that's what I'm going to talk to you about today, the science of chemistry. So what is chemistry? Chemistry is the science of substances and how they turn into different substances. And very frequently, we can recognize a chemical change because there is a change of color. As I pour my water from one flask to another, you'll notice it's changing color. And the reason why it's changing color is because every time I am making a new substance. Thanks to the science of chemistry, we live in a fantastic world today. Many products that we use on an everyday basis are thanks to the science of chemistry. Chemistry, the science of substances turning into different substances. Thanks to the science of chemistry, we have drinking water from the tap. We have plastics, polymers. We have glues, adhesives, explosives. We have detergents. We have toothpaste. We have washing up liquid. We have fuels. We have agricultural chemicals. We have an amazing range of extraordinary substances thanks to the science of chemistry. Chemistry, the science of substances and how they turn into different substances. And in these few experiments which I have showed you, my dear friends, I have given you an example of a chemical change which takes place and can be recognized because there is a change of color. Now, I have shown you experiments in which there is just simply one color change. I will now show you something very special. And I have this in this flask here. I have here what the magicians call magic rainbow water. Now, the reason why they call it magic rainbow water, obviously, is because it can change to all the colors of the rainbow. And I'm sure you know what those are. Red, orange, yellow, green, blue, indigo, and violet. So we've got green to start with. Now, if you don't mind, I'm just going to rearrange things just a little bit on my bench in order that you can see the experiments a little more clearly. So I'm just going to wipe up a little spill here. I'm going to move my flasks around like this so that we can be able to watch the experiments with a greater degree of clarity. So put my cloths over there, and so we now have put at the front of our bench the so-called magic rainbow water. So let's see whether we can make this magic rainbow water change color. I'm going to add here a few drops of one of my chemical liquids like this, you see, and remember it started green, and you see nothing has happened. Oh dear, there seems to be no chemical reaction, but we give it a little swirl around, you see, and unbelievably there it is. The color has changed. It is now yellow. Clearly, a chemical reaction has taken place. We now add a few more drops here, and we give it another swirl around and see whether this does anything. And now you see the yellow color is going darker. It is in fact approaching this color here, which is orange. we have now a light orange color. As we add another drop or two, the orange will get darker. There it is. There's a beautiful orange color there. And now, if we add a few more drops, we can then hopefully get maybe another color. Give it a little swirl around here. And now you see we have a beautiful red. So, we've observed 3 color changes from green to yellow to orange to red. And you see, we could say this is magic, but of course it's not. It's chemistry. And because this is a chemistry lesson and not a magic show, I am going to tell you exactly what I have in this flask. Well, obviously it's mainly water. It's mainly water from the tap, but to the water I had added a small amount of this substance here, which is called universal indicator. It's something that you'll meet in years 8 and 9. We all use it. All children in the round world use it. It's one of those wonderful inventions of the science of chemistry. Now, the word universal means it can be used for all liquids. The word indicator means it indicates things, and it shows things, obviously, by changing color. But the next thing is, what has it been indicating? Well, obviously, it's been indicating this, which I have been adding to it here, which is called hydrochloric acid. This is an example of many types of acid that exist, and hydrochloric is this particular one. And you may be interested to know, how is this relevant to everyday life? Well, I'll tell you, it's very relevant because all of us have this acid in our digestive systems. A very dilute form of hydrochloric acid exists in every human body, and the reason why it exists, it helps us in the digestion of our food. And it's in a dilute form, and the reason why, as I said, it breaks food down in order that once you've eaten your food, it's in your stomach, it's broken down, and therefore it gives us energy to do lots of things, and also the necessary components to make our bodies grow. So that's hydrochloric acid. But now let's turn to opposites. If we talk about very, very simple and basic opposites, like what's the opposite of long? It's short. What's the opposite of hot? It's cold. But in a chemical sense, an acid has an opposite. And in this particular case, the opposite of an acid is, I hope some of you might know, is called an alkali. And I have an alkali here which is opposite to an acid. Many alkalis are known as well, but I wanted to tell you this particular one which I've got here is called sodium hydroxide. And what's this used for? Well, I'll tell you, it's used for making soaps. If you have a bar of soap at home, you wash your hands with a bar of soap, that will have been made from sodium hydroxide. And I've got another surprise for you. This has been known since ancient Egyptian times. Already 5,000 years ago, people were making soap from sodium hydroxide by boiling it with oils and all sorts of other things. So let us now see, if I now add sodium hydroxide to this universal indicator in water, we should be able to reverse the color changes as the sodium hydroxide reacts with its opposite, which is an acid. So we're now adding a small amount at a time, and hopefully the color will go from red to orange, because that was the previous color. Give it a little swirl around, and there we see we now have a beautiful orange color. Now, the indicator is showing us that there is a chemical reaction taking place. It's indicating the reaction between hydrochloric acid and sodium hydroxide. And then we have beautiful yellow color which is there. Now, this type of a reaction between an acid and an alkali has a special name. I wonder if you know what it is. It's called neutralization. In this reaction here, I am neutralizing the hydrochloric acid with sodium hydroxide, and I can tell that because the color of the universal indicator is changing slowly back to green. Now water, of course, is neutral. It's neither acid nor alkali. And that's what the universal indicator shows us. But here you see, we've just about reached the neutral color. It's green there. Now at this stage you might like to say, well, when they have reacted together, these two, and become neutral, what have they made? Any guesses? Hydrochloric acid and sodium hydroxide. They're example of an acid and an alkali, and when any acid reacts with any alkali, it always makes a salt. And what I made in here is actually the salt, which is called sodium chloride. So I've made sodium chloride, which is the same salt that is found in seawater, and it's the same salt that is used in our food, and it tastes salty. So if someone was to say to me now, does this taste like seawater? The answer is yes, it does. It would exactly taste like seawater. Obviously, I'm not going to taste it or drink it. And the reason is very simple. It's contaminated with universal indicator, which, although not poisonous, would nevertheless contaminate the result. So we're here at the point of neutrality. We've made sodium chloride from sodium hydroxide and hydrochloric acid. And now let's continue to add more sodium hydroxide. So what we're doing now, we are now making a solution have an excess of alkali. And you see, the solution has now gone to I've actually probably added a tiny bit too much because it's gone to quite a dark blue. I'm trying to get a sort of a turquoisey green color. So I've just reversed that a tiny bit. So there you can say it's gone from green to a turquoise green, coming up basically to blue. Let me just now add, I have to add these very carefully because I don't want to miss the colors. You know the colors, the rainbow, red, orange, yellow, green, blue, indigo and violet. So there's our blue. Now indigo will be a slightly darker blue, basically halfway between obviously blue and violet, and I think we can settle for that being indigo there, and then a further dose there, we now have a significant excess of alkali, and there you see a beautiful violet color there. So here you see another example of how we can study chemical reactions or know that chemical reactions are taking place because there is a change of color. I'm going to put this aside now on the side here. I have now introduced you to the science of chemistry. I've told you what it is, the sciences of substance, the science of substances turning into different substances. And having showed you that we can often recognize this by means of a color change, I am now going to turn to my favorite topic, and that of course is fire. And I'm going to show you one of the most ancient chemical reactions that has been known and much loved by us human beings, and it is a flame burning at a candle like this. Now this type of flame which you see here represents a chemical reaction, of course. It does have color changes. We're not going to go into those in great detail today, but the important thing to know about this flame is, the first thing is, it's a type of flame that has been known for over 100,000 years by humans. For it was over 100,000 years ago in East Africa where the first civilized human beings, where first ancient intelligent man used to live, that people were able to make a flame like this and to sustain it. They made the flame either by striking flints or by twiddling sticks to generate a huge amount of friction. And this type of flame is the only type of flame that was known to human beings for tens of thousands of years, until that is about 250 years ago, when chemists made some most remarkable discoveries about the way that fires burn. If you don't mind, you notice I've just accidentally blown my flame out, so I'll just relight it, because obviously to be talking about fire and not having a flame would be a complete disaster. So there we are. There is our flame burning once again. And what I wanted to show you in the next few minutes is how, thanks to the achievements of modern chemistry, we now have a wide variety of flames that can be put to a great different range of uses. I'm going to start off by showing you a sort of a pyrotechnic effect, which To call it, what the magicians call it, is called magic volcano powder, because this really does resemble a miniature volcano. And I have my mat here, my fireproof mat, and I'm going to put some of my magic volcano powder, as the magic man calls it, magicians call it, and I'm going to place it on my mat there. Now, if you don't mind, I'm going to place this on my mat here, and I'm just going to move things around a little bit, partly in order that you can see things better, but partly for my own safety and security. Now, as you know, this is not a magic show. To call this magic volcano powder, it certainly will resemble a volcano, as you will shortly see, but that, of course, is not the object of today's chemistry lesson. It is tell you the truth and nothing but the truth. So, I'm going to put this on my tripod here and put it there. And before I set fire to my magic volcano powder, I'm just going to do a little more rearranging of my bench. So if you excuse me, there we are. I've just put a few more things. I'm putting things to one side, obviously, because I have to be well organized in order to conduct things for you effectively. So there it is. Some of it's a little bit lumpy, but the honest truth is that doesn't matter. The volcano will take place effectively. And I wanted to tell you next what it actually is. Okay, from the magician's point of view, it's magic volcano powder, but the honest truth is, it is called ammonium dichromate. And I've got it here in this container here. Ammonium dichromate. Now, one of the most important things when we handle chemicals is to know what the parameters are for handling it. In other words, what you have to take care with in order not to do something wrong. And for that purpose, we have invented something which are called hazard symbols. You can see them there on the back of this flask, of this container, should I say, and they're pictograms which show various symbols of things you have to be careful with. So I'll just very quickly go through them. Top left-hand corner is a flame. That shows it's an oxidizing agent, makes things burn. Top right-hand corner shows you a liquid corroding your hand, so that means it's corrosive. Potentially, if you dissolve it in water, it'll give you burns and ulcers. The skull and crossbones in the middle, that tells you it's a deadly poison, so you don't eat it. Bottom left-hand side, a picture of a star on a body, potentially a carcinogen. On the bottom right hand side is a picture of a dead fish and a dead tree. That is an environmental hazard. So in a nutshell, this is something that we have to take great care with and respect. It doesn't mean you can't do experiments, but it means you have to take great precautions. And I've taken them. I've taken them by allowing lots of space around. And what's going to happen once I set off the volcano, I will hold it up in the air to allow it for you to see it, and then I will move it backwards. I will move it backwards and put it in the cupboard over there. And I will then explain to you the important chemistry, because remember, we're talking about chemistry, the science of substances, and how they turn into different substances. So, if you don't mind, I'm just going to put my splint in there, and as soon as it starts erupting, I'm going to hold it up, and I'm going to come just a little bit more forward there, and allow you to watch carefully. If you don't mind, I'm just going to blow my splint out, if I can, but please look at the volcano and not at me. And there it is. You can see clearly an eruption is taking place. There are sparks coming off, and there is a significant shower of a dark ash, a dark colored ash. I don't know whether you've watched the news recently, but a very large volcano erupted in Indonesia, and there was some amazing footage of that, slow motion, showing the huge cloud of smoke rising high in the air. Now, this particular volcano doesn't, of course, produce any smoke, and otherwise I would be very uncomfortable, nor indeed does it produce any toxic gases. Once again, I would be very uncomfortable. So what has it produced? Well, it has produced two gases which have gone into the air, which we can't see. One of them is water vapor or steam. Could you believe it's coming from there? Yes. And the other one is called nitrogen gas, which is the main part of our atmosphere. So that has gone inside, has come out, And the black solid which is left behind is nothing other than chromic oxide. And that too is a relatively harmless chemical. Obviously, I wouldn't want to be breathing dust in, but I'd nevertheless, and that's why, of course, I've put it in the cupboard there. And I'm going to just, if you don't mind, just going to blow the dust off. Et voila. I'll be sweeping the floor, obviously, afterwards. So that's why, now why do we demonstrate that? Well, obviously, it is an amazing experiment. It's a different type of flame from this flame here. But also, it illustrates a very important type of chemical reaction. You see, ammonium dichromate is quite a complicated substance. Its formula is NH4 twice Cr2O7. You don't have to remember that, but the point is it's made up of lots of different atoms chemically combined together, those orange crystals. Now, during this reaction, they break down. Ammonium dichromate breaks down into simpler substances, and I've said what they are: water vapor, nitrogen, and chromic oxide. And those substances are simpler than the ammonium dichromate. And because they are simpler substances in terms of the number of particles they're made, etc., we call this type of a chemical reaction in which a complicated substance breaks down into simpler substances, we call it a decomposition. So the ammonium dichromate has decomposed into nitrogen, water vapor, and chromic oxide, and you will certainly be meeting many more decomposition reactions when you study chemistry in school. Now, having shown you the first type of fire which I wanted to introduce you to, I wanted now to show you something which we burn on an everyday basis, but perhaps we don't think too much about it. And here it is, it's in this bottle here. Now, what I've got in this bottle, hopefully you won't recognize it, it's nothing other than petrol. You see, we burn petrol in a motor car engine every day. You drive your motor car up to the filling station, you fill the petrol tank with petrol, you turn on the ignition, brum, 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 brrrr, and we drive away. And I have to tell you, I love driving a motor car. And the reason why, well, because I don't do anything. I just sit there, press on the pedal, and off goes the motor car. So this is, for me, fantastic fun. But why does the car go forward? The reason is because petrol is burning inside the engine. And that's what I wanted to talk to you about for the next few minutes. I wanted to start off by telling you something that you all know. And that is motor cars are a modern invention. They were only invented about 130 years ago. But petrol is a substance, similar substances to petrol have been now known for thousands of years. Why is that? Well, because out of the ground in many countries there oozes a dark black liquid. The countries I could tell you are, for instance, are India, the Arabic countries, China, Venezuela, and the Ukraine and Poland in Southeast Europe, but many others as well. And in those countries, a black liquid comes out of the ground, which is clearly not water. Now, in the olden days, people used to call it black smelly water because it had a foul smell and it had a black color. But people have always been curious, and they did all sorts of things with it. They put their fingers in this black smelly water, they smelt it, they tasted it, it was disgusting. But one of the things they learned to do very early on, we know, they learned to distill it. They boiled the liquid and they collected the vapors and condensed them back into other liquids, condensates as we call them, or distillates as we call them today. Now that was particularly well known in the Arabic and the Chinese world, where archaeologists have discovered the remnants of ancient distillation equipment. And what I wanted to tell you, people would have known substances similar to petrol thousands of years ago. So I am now going to do an experiment for you, which might have been done by somebody a few thousand years ago, a few hundred years ago, a few thousand years ago, let's say, who was just saying, oh, that's interesting, I've got this stuff coming out of my black smelly water, what does it do? So I'm going to set some petrol on fire and ask you to ask yourselves, do you think that this is the way that petrol might burn in a motor car engine. So, what I'm going to do, now what I have to start off by telling you, petrol is very, very dangerous. It's amazingly flammable, so we only ever have a very small amount at a time. And what I'm going to do is use my teat pipette to squirt some onto my fireproof mat here. I will then replace the lid on my bottle here to make sure that accidentally we don't get what's known as a flashover. I shall then use my wooden splint and set fire to the petrol. So please watch carefully. So there is a small quantity of petrol going on there. I'm squirting it on, rapidly replacing my lid there, and now we are applying our splint. We're now applying our splint, so watch carefully. Do you think this is the way the petrol burns in a motor car engine? No, no way, Jose. You could see it. A yellow, smoky, slow, and look at all the horrendous smoke coming from that. A yellow, slow, smoky flame. This is not going to make a car do 100 miles an hour down a motorway. But let us now do some very elementary scientific thinking. Look, wood burning, yellow flame. Petrol burning, yellow flame. Wax burning, yellow flame. That means there must be something similar about those three types of flame. And allow me to show you, my dear friends, I can show you this something similar by means of this beautiful white porcelain evaporating basin. I am going to now put this over my flame here. And as I hold it over my candle flame, not only is the evaporating basin getting hot, but you'll notice it has also acquired a black deposit on the bottom. Now that black deposit is called popularly soot, but it is also the element carbon. The element carbon, which is one of the most important building blocks of nature, it's a chemical element, and it's the main building block, of course, of living things. And I wanted to tell you that carbon, therefore, which we see coming off from, and all of these yellow flames will produce this, carbon is chemically combined in wood, which is a carbohydrate, a natural polymer called cellulose. It is chemically combined in petrol, which is a mixture of hydrocarbons, and it's chemically combined in wax, which is a mixture of hydrocarbons as well, but the molecules are larger. And in each of these combustion processes where you see a yellow flame, soot and smoke are produced. And for that reason, the chemists call this type of burning incomplete combustion. The fuel hasn't fully burnt, we've still got some carbon left over, and we could burn that as well. But there's simply, the air was not plentiful enough to get this to burn completely. I will now show you how, thanks to the science of chemistry, the petrol burns completely differently inside a motor car engine. Now I have for this purpose a tin can here, which I'm holding up for you here, and the tin can has a tightly fitting lid and there is a hole in the bottom there. And what I wanted to tell you is that inside a real motor car engine, the petrol is set on fire with one of these, which is a spark plug. That's a genius invention of the science of physics. What I am now going to do is to show you how petrol burns inside a motor car engine. And why have I got a tin can? Well, all motor car engines, as I'm sure you know, are called internal combustion engines. Internal inside, combustion means it burns. Engine, it's something that does useful work. And the spaces where the burning of the petrol takes place in the engine are called cylinders. And this tin can has the shape of a cylinder. But inside the cylinder, in a motor car engine, there is a tightly fitting component which is called a piston. Now, I don't have a piston which can move up and down in this cylinder. I have a tin lid which fits very tightly. But I do have a real piston from a real motor car engine. And here it is. This is what Every single motor car engine in the world has these inside. This is a piston. It fits tightly into the cylinder. It goes up and down in reciprocating linear motion, and this connects to the crankshaft via the connecting rod, which turns around and makes the car go forward. So that is an example of a real piston. I'm not talking about mechanics today. I'm focusing on the chemistry. So if we now turn to our can, and you'll notice there's a hole in the bottom there where I can set fire to my petrol. If I now take a can and came up to someone and said, hello, can you tell me what's inside this can? When you look inside, you see it's empty, it had paint in it, it has no paint. Correct, it's an empty can. However, from a point of view of burning, what's inside this can? We have a completely different answer. It's full of something that's needed for burning. And that full, my dear friends, is of course the air. It's all around us. It's full of air. It was the chemists who first recognized the vital role of air in the burning process. So allow me to show you now how we can actually use this knowledge of the chemists by placing a carefully measured quantity of petrol inside our can. Now I do repeat, this has to be done pretty accurately. I've done this quite a few times before, so hopefully it will be accurate. And I'm going to squirt this petrol inside. Now I have to tell you, safety first, I have to put the lid on the can here. I have to put the lid on the can, on my bottle. Sorry, I'm getting confused. And I'm now going to squirt the petrol inside here. So I've squirted my petrol inside here, and now we are going to close the can, by just using my elbow to a couple of times, just to make sure that the lid is on very firmly. So there we have, our lid has now been placed firmly in there. So you saw it with your own eyes. I put some petrol in there, and it was in the form of a liquid. What I wanted to do now is I wanted to warm the can up a little bit, and I'm warming it up with my cheeks. I'm just warming it up a bit like this, and that is in order to speed up a most important change which is occurring to the petrol. And that change is not a chemical change. It's not, the petrol is not going to burn. The petrol is not going to change into another substance. It is undergoing a physical change, a change of state. You see, petrol is in the state of a liquid, and there are three important states of matter which help us to understand how the world works: solid, liquid, and gas. And most pure substances can be made to exist in all three of those states. So by warming this up, the petrol which I have placed in here has evaporated, it's turned into a gas. And as it has done so, it has mixed with the air in the can to form what we call an homogeneous system. It's fully mixed in. I am now going to set this on fire. I'm going to place it on a tripod there. I'm going to set it on fire, and I want you to watch carefully what's going to happen. I'm just going to get my wooden splint, and I shall put a flame underneath. And watch carefully, see if you can spot the color of the flame and indeed any other effect which might be visible. So here we go. I don't know what you saw, but you heard at least a little bit of a bang, and I'm sure you could see the lid has gone. The lid, of course, flew to the ceiling. And that was a very rapid combustion indeed. I'm sure no one will dispute the fact that this type of burning could certainly make a car do 100 miles an hour down a motorway. Now, why is that and what's happened? By the way, notice there was no smoke, no yellow flame, and if you notice the color of the flame, it was blue. And that blue flame represents what we call complete combustion. There is nothing left over. It was the chemists who were able to understand the role of air in combustion and had understood already 250 years ago the vital idea that air is a mixture of gases. And the two gases, when the petrol burns, it makes two gaseous products, carbon dioxide and water vapor, which is H2O. And the reason why it makes those two products is because the part of the air that's used in burning is, of course, called oxygen. And air only contains 1/5 of oxygen. Now, when scientists who'd made this remarkable discovery about 250 years ago, they got terribly excited. They said, brilliant, let's now use pure oxygen to make even better fires and even brighter fires. And so they did. And there were two ways in which oxygen was used to make fires burn better. You could either mix the fuel with oxygen physically, or you could chemically combine the fuel with oxygen to make it burn better. And I will show you an example of both. I'm going to start off by showing a remarkable effect that was achieved by combining a fuel with oxygen. And the fuel which was used, something you never ever guessed could be used as a fuel. It's one of the most ancient substances known to humankind, cotton wool. Cotton has been known and grown and cultivated in the great ancient civilizations in India 5,000 years ago, and also in Central America where Mexico is today. Those were the cultures who were able to grow the cotton plants, they were able to extract the cotton and then to make beautiful fabrics from them. No one would ever dream of burning cotton to keep warm or to cook your food on. They used it for making fabrics. But in the middle of the 19th century, when German chemists were beginning to understand substances which are found in living things, organic chemicals, what we call them, they recognized that cotton wool and wood are exactly the same substance, cellulose. And so they started developing techniques for combining these with oxygen to make it burn better. Allow me now, first of all, to show you how a piece of cotton wool burns in air. I have to warn you, this is a dreadfully boring experiment. You see, it just burns like this. It just burns like this. It's because air only contains 20% oxygen, and so therefore this burns slowly, it smolders. It's what we call incomplete combustion, and very shortly the tiny little bits of ash will drop off. You'll be able to see a little bit of smoldering there if I hold it a little closer, and there you see that is cotton wool burning. I'm going to drop this on the floor now, by the way, just because I'm in a little bit of a hurry, so watch it fall away, and maybe it won't fall. Oh dear, it's sticky. There we are, bits are falling off. Now those are bits of uncombined, they're just bits of ash which are left over. But that, you see, dreadfully boring, nothing at all to write about. Now, write home about. So if you don't mind, I'm just going to put the flame out now, just to make sure that we have a nice clean sample here. And I am now going to show you a piece of cotton wool which has had extra oxygen added to it. I'm going to take it out of my special box which I have here. And I wanted to show you how it looks. This has been chemically combined with extra oxygen in order to make it burn better. And I just wanted to show you this effect and see whether you can spot the difference. So I'm going to hold it over my candle flame. By the way, if you don't mind, I'm just going to tidy up the little bit of water which I made a mess with here. So excuse me, I do like to keep, most importantly, one must keep the laboratory tidy. I'm going to now very quickly just show you, place my candle here and show you how this cotton wool, which contains extra oxygen, it looks the same as that, but actually it weighs more. One of these weighs 1.7 grams. This, which I have made, it weighs 2.4 grams. It contains extra 0.7 grams of oxygen chemically combined. Watch how this burns and see if you could spot the difference. And as you see, an instantaneous flame. Nothing was left over, no smoke, no slowness, as you just saw. Now, the first person who did that was Professor Christian Schönbein. He was professor of chemistry at the University of Basel in Switzerland, and he conducted this experiment in 1846. What he had actually discovered was the world's first high explosive. It's called nitrocellulose gun cotton for short. I won't go into details, but I'll tell you one thing. He got terribly excited. He went, whoopee, brilliant, I've done something really amazing. And he'd, as I told you, discovered the world's first high explosive. Now, I would like to show you an explosion, but that would be foolish in the extreme. But I'll show you something instead. I will show you something else instead, and that is a propulsion, which is a controlled type of explosion, which I have here. Here I have a mortar. This is an old style. It's like a cannon, and it's used in the great fireworks displays to throw fireballs, etc., into the air. And what I'm going to do, I'm going to use a piece of gun cotton as a propellant to shoot some ping pong balls, which I've got in here, out into and hit the ceiling. So we'll see whether they hit the ceiling and come back down again. So I've got 4 ping pong balls here. I have in here, I have what I call a cage. This is a special cage where I shall place a small piece of my gun cotton or nitrocellulose, and then we shall set it on fire and see whether the ping pong balls are projected satisfactorily and whether they can hit the ceiling. So we're going to now place one piece of our cotton here. This is, as I said, it's not cotton wool, it's what we call, technically it's called gun cotton. There it goes. I'm going to drop it into the bottom. Please watch carefully. There's a hole at the bottom where I shall light my fuse. Listen carefully. There we are, that clang, that tells you that it's gone in. We now put in our 4 ping pong balls, 1, 2, 3, and 4. And then what we shall do is we shall now make a tiny fuse here, and we shall place it inside the hole there by using our special piece of our special tea pipette here. I shall push this inside here, and then hopefully that will be touching there we are. It's gone right through inside now. And what I'm going to do now is to set fire to it, and hopefully it's standing straight, but I will nevertheless put this on here. I will put this on here, and I shall apply a light to it, and hopefully you will see the ping pong balls go shooting up into the air. So please excuse me, I'm just going to put on my goggles here. This is just in case some debris goes in the wrong direction. We shall apply a light, and then we shall see whether, hopefully, you probably won't see, but let's see whether the ping pong balls come shooting out. 3, 2, 1, fire. Well, I don't know what you saw, but I could see lots of dust and fluff flying around. The ping pong balls definitely came out. So an example of the remarkable achievements of the science of chemistry, in which we have been able to exploit our knowledge of chemistry for the benefit of mankind, thanks to our understanding of the remarkable fact that air is a mixture of gases. What I'm going to do is just show you a couple of more experiments, and then we shall stop. So what I've got here is, you see those beautiful 3 glass balls, one on top of another. Now they constitute what's known as a Kipp's apparatus. It was invented by the Dutch pharmacist Petrol, and he was wanting to invent a way of making a gas by reacting a solid with a liquid. So in this jar, excuse me, I'm just going to move this out of the way. In my flask here, I have got hydrochloric acid here, I've got marble chips there, and I've got a series of night lights. Now I'm going to move them all away so that you can just see, and I've got a jar here. I'm going to open this. Now as I open my tap here, you'll see that the hydrochloric acid, goes from the top to the bottom, and then it will start to cover the lumps. These are white lumps of marble calcium carbonate. And as they start to cover it, you'll notice it fizzing, it vigorously fizzing. And you can see nothing. And the reason is there is a gas coming out which is invisible. And it's another gas which is present in air. It's called carbon dioxide. You can't see it, but look what it does to our burning splint. Lower the burning splint, and the splint goes out. And the reason is very simple. Carbon dioxide is heavier than air, and it smothers the flame. It prevents it from burning. That's why carbon dioxide is used in fire extinguishers. And now I'm going to attempt my most difficult experiment of all. bubbles floating on carbon dioxide. Absolutely amazing. Those bubbles are full of air. And the last one has just gone out, but there's still plenty of carbon dioxide. Regardez attentivement. Carbon dioxide used in fire extinguishers. It's the gas in our fizzy drinks. And just to finish, I have two more experiments. In this balloon here, I have the lightest gas in the universe, which is hydrogen. I'm going to set it on fire, and then after that, one more, and we shall be done. So, is that visible to everyone? Can we just double check? Sorry, I've got... it's going to go down a little. Please excuse me, dear children, we're just going to lower it a bit. That's still too high. Still too high? Right, let me just lower it. We've got to get you to be able to see this. This is the hydrogen, the lightest gas in the universe, and it burns to make pure water. I will now set this on fire. Is that okay? Good. So, we're going to set this on fire. I'm just double checking. When we do these experiments, it's imperative that there's nothing in the oil that could burn. So, I'm going to set this on fire. Notice the beautiful bright orange flame. It doesn't make a bang, it makes a thud. Watch carefully. That was pure hydrogen burning in air, and it makes a tiny little bit of water. But in this balloon here, I have a mixture of hydrogen and oxygen. Now when this burns, this will make a very loud bang. And this very loud bang is caused by the fact that the gases are mixed in exactly the right proportions. The French philosopher, natural scientist, Pilatre de Rosier used to call this aria tonante. In Italian it means thunder air. Now that will be my last experiment, and please watch and listen carefully. It makes a very bright flash. That's the thing to look for, as well as obviously a very loud bang. So there it is. I hope you noticed the flame went out. Thank you very much for your kind attention, and I wish you all the very, very best for the future. Thank you.